Look at this anomaly. A multi-thousand-ton kinetic mass slicing through the Savannah, elevated 50 feet in the air. This isn't just a bridge. It's a structural bypass of an entire ecosystem, maintaining linear velocity while the world below remains static. To any seasoned infrastructure analyst, the data is staggering. 300 miles of Grade 1 rail, commissioned and operational in under 36 months for $3.8 billion. In states like California, that budget barely covers the environmental impact reports and 5 miles of grading. We are witnessing a temporal distortion in project delivery. But we aren't here for the geopolitical noise. We're here to deconstruct the applied physics. We're talking about the geotechnical mastery required to stabilize a high-speed corridor through the Great Rift Valley, and the metallurgical integrity needed to resist thermal expansion in 100-degree heat. Before this, the friction was literal. The old colonial line was a localized supply chain nightmare. What should be a 4-hour transit was a 48-hour crawl. In the calculus of macroeconomics, that delay is an entropic force, a drag coefficient that was effectively strangling Kenya's GDP potential. Enter the China Road and Bridge Corporation. They didn't just export capital, they deployed a vertically integrated industrial army. In the macro view of global logistics, this isn't just a train, it's an infrastructure multiplier designed to hack the traditional limitations of African trade geography. While the US spends a decade on environmental litigation, they deployed orbital LiDAR to bypass ecological dead zones. We are talking high-resolution topological telemetry mapping every structural requirement for all 300 miles of track in months, not years. Here is the geotechnical nightmare. The African Savannah is a sea of loose silica. Drop a 100-ton concrete pillar here, and you get a catastrophic shear failure. Under kinetic stress, this soil undergoes liquefaction, turning solid ground into a structural liquid that swallows infrastructure whole. You cannot build a multi-billion-dollar megastructure on a microscopic matrix of air and loose sand. So the engineers hacked the ground itself. They didn't just dig, they initiated dynamic compaction, a process of forced densification to rewrite the soil's load-bearing capacity. First, they introduced water via massive articulated spraying arms. In soil mechanics, precise moisture content acts as a binding agent, increasing the capillary tension between sand particles. It's about turning a powder into a cohesive structural substrate. Then came the kinetic bombardment. Cranes dropped steel weights, each the mass of an M1 Abrams tank in hyper-precise grids. These drops generate subterranean shockwaves, collapsing the air pockets and forcing the geological lattice into a permanent, rock-hard state. These shockwaves force the air pockets out of the soil matrix. We're talking aggressive densification. The ground transitions from a soft, porous material into a foundation with the tensile strength of solid bedrock. This is the antithesis of the settling foundations that plague our US transit projects. Then came the static phase. Rolling machines exerting immense hydrostatic pressure pressed the signature Kenyan red soil layer by layer. The engineering tolerance here is microscopic. A 1% deviation in density means a high-speed derailment down the line. Precision is the only currency that matters here. Quality control was a continuous feedback loop. Geotechnical engineers ran non-destructive seismic tests on the sub-base daily in 90-degree Fahrenheit heat. They weren't just laying tracks, they were transforming the Earth's crust into a stabilized industrial platform capable of supporting millions of tons. But the ground was just the launch pad. What rose above it was a concrete leviathan. Imagine thousands of 50-foot pillars, each weighing 90 tons, spaced at exactly 1 5-foot intervals. While we argue over zoning permits, they were deploying a modular army of stone. This isn't standard concrete. This is high-strength, steel-reinforced structural concrete engineered for extreme dynamic loads and massive thermal expansion under the relentless equatorial sun. It's a metallurgical and chemical masterpiece designed to stay rigid while the world melts around it. While Western infrastructure projects rot in regulatory purgatory for decades, the Chinese assembly line is churning out 100-ton precast, pre-stressed concrete girders with terrifying efficiency. These aren't mere structural components. They are high-mass behemoths optimized for maximum load, bearing through advanced internal tension mechanics. The physics here is a masterclass in counter-stress. High-tensile steel cables are stretched to the limit inside the mold before the pour. Once the concrete cures, these cables attempt to contract. creating a permanent compressive force. This internal squeeze allows the girder to resist shear forces that would snap ordinary American reinforced concrete like a toothpick. To bridge the gap, they deployed the Launching Gantry, a 600-ton bipedal machine that looks like it stepped out of a sci-fi shipyard. It literally walks across the pillars, lifting these 100-ton beams with millimeter precision. No cranes, no ground-level staging, just pure mechanized dominance over the terrain. By elevating the entire corridor, they neutralize the biological variable. While US highways create death traps for local wildlife, Kenya's megafauna corridors remain completely unencumbered. Elephants maintain their migratory paths below, while hyperlogistics move at 75 miles per hour above. It's total ecosystem integration. Now, let's pivot to the metallurgy. The rail itself begins as multi-ton steel billets, blasted in industrial furnaces to a white-hot 2,200 degrees Fahrenheit. This isn't just about melting metal, it's about altering the molecular lattice to survive the brutal thermal expansion cycles of the African sun. Observe the recrystallization phase. At these thermal states, the carbon steel lattice enters a plastic regime, allowing us to manipulate the grain structure. This isn't just forging. It's a high-pressure extrusion through rolling mills that crafts a continuous profile base, web, and head with atomic-level consistency across the entire cross-section. Standard timber is a relic. We're deploying high-performance pre-stressed concrete sleepers. Think of these as kinetic energy sinks. They are engineered to dissipate the vibrational energy and inertial load of a 20,000-ton freight consist, decelerating from 50 miles per hour in the equatorial heat. Run the numbers. 2,700 sleepers per mile across a 300-mile stretch. That is over 800,000 units. While American infrastructure projects get bogged down in multi-decade procurement hell, this was a masterclass in decentralized logistics, coordinating millions of components with a zero-defect tolerance and just-in-time delivery. To achieve this deployment velocity, they utilized modular assembly. By pre-clipping the rail to the sleepers at specialized depots and dropping 5 0-foot modules into place, they effectively turned civil engineering into a high-speed assembly line. It's a pace that renders traditional Western construction models obsolete. But here is the engineering endgame. Traditional bolted rail joints are structural liabilities. They create harmonic resonance and thermal wear points. The solution? Eliminate them. We are talking about continuous welded rail, turning 300 miles of track into a singular monolithic thermal mass. Enter exothermic thermite welding. By igniting a stoichiometric mixture of aluminum powder and iron oxide, they trigger a localized chemical cascade hitting 4,500 degrees Fahrenheit, nearly half the temperature of the sun's surface. This superheated liquid iron inundates the gap, fusing the railheads via molecular diffusion. The result is CWR continuous welded rail. It is a monolithic steel ribbon spanning 300 miles, engineered to be entirely immune to the vibrational degradation that would tear traditional jointed tracks apart. The macro result? A logistical nightmare that once took an agonizing 24 hours is compressed into a 4-5-hour high-velocity transit. By slashing supply chain friction, they haven't just moved cargo. They've optimized the economic throughput of the entire East African corridor. You can debate the geopolitics and the debt structure until the sun goes down, but from the cold perspective of metallurgy and geotechnical execution, this is an absolute masterclass in brute-forcing physical reality to match a digital blueprint. It is efficiency at a scale the US has struggled to replicate for decades. If you appreciate the uncompromising science behind global megastructures, hit subscribe. And here is a question for the analysts in the audience. If the US were to apply this level of extreme modular engineering to one failing piece of our own infrastructure today, where would you start? Let me know in the comments.